Well, good afternoon, everyone. Uh, Thank you for joining. Today we have Gia, who's a postback scholar here in Kepler, working with Tomar, right?
Yes, Tomer.
Tomar Elman. Um, she's going to give us some insights about this paper on causal abstraction. Uh, just quick logistical things. I'm assuming people would have signed up on the sign up link on the Slack channel. Is there anybody here who's not on the Slack channel? I'm on the channel. Yeah. The link is still active. The only thing is, if you are eating food, please sign up because that's how we pay for it. So if you sign up, our budget is maintained. With that, I'll let Gia take it away. Go ahead,
Okay.
Gia. Floor is yours.
Hi, everyone. Thank you for having me. So, today I'm going to talk about this paper by Atticus Geiger et al. Causal Abstraction, a Theoretical Foundation for Mechanistic Interpretability. And it came out in the Journal for Machine Learning Research this year, but a preprint was out a while ago. And it's mostly out of the Chris Potts, Thomas Icard, Noah Goodman group at Stanford. And Atticus Geiger is now at Goodfire. So mechanistic interpretability has accumulated into, over the last couple of years, accumulated into this huge pile of methods, patching, SAEs, causal, scrubbing, probing, steering, and more methods. And what it hasn't really had is a shared theory that would tell you what any of those methods are actually claiming, or lets you compare one against the other on the same footing in the same shared vocabulary. So what this paper is trying to do, or give the field, is what causal inference gave epidemiology many years ago with Judea Pearl. That is a formal object you could check a claim about interpretability against. So we're going to start with a kind of philosophy of science about explanation and then work our way through some abstract algebra, and by the end I'm hoping to connect that to MechInterp. So the, I guess, founding or starting question of this inquiry is, why does a neural network resist a clean, faithful, high-level story about what's happening inside the model in the first place? Well, I'll start with an idea that is kind of easy to lose sight of. That is, we're not really missing any information here. Every forward pass through one of these machine learning models is completely accounted for by its weights and its activation functions. And there isn't this hidden variable or something unmeasured that's going on inside that we don't know of because we're making the model. So in a very technical sense, we already have the whole causal story. But if that's true, then what's hard isn't the, access to the model internals, but how legible it is to us. Which means the real job of mechanistic interpretability is to find something smaller or more general, I would say, this human understandable causal story that's still then faithful to what large language models and deep learning models are doing or producing. And I guess the word faithful is in some ways where the trouble is, because we already know the failure mode here really well. You could always construct a tidy little story about what's happening inside the black box that sounds right, or correlates pretty well or accurately without it having any real purchase on what's happening inside. And the authors call this the just so story problem. So in some sense, the entire rest of the paper is an attempt to make this word faithful precise enough about what's happening in the model so that you could actually be wrong about it, that it could be falsified, rather than just more or less persuasive in an explanation. So that framing should sound familiar, because it's basically Mars levels from cognitive science, and it's the same problem that they've been sitting with for decades. So you can describe a mind at the level of biochemistry, for example, or you can describe it purely in terms of input-output behavior. And neither one of those is actually where I would say the more interesting explanatory work is happening. The useful level is the one that sits between, at the algorithmic level. And what's also interesting is that deep learning has recreated this exact stack. So the weights and activations at the bottom, and then some input-output function at the top that's the observable behavior. And the missing middle layer, you would call it circuits or features or concepts, if you will, that's very much what we would like to formalize using this framework. And so I'll flag that. But it's also, this is one of the areas where the authors think the analogy breaks down, and I'll come back to that later in the presentation. So given all of that, the paper does three fundamental things. First is them taking an existing theory of causal abstraction, which up to now has really only handled clean interventions, like fixing a variable or swapping out its mechanism for a fixed replacement. And then they generalize it to these arbitrary transformations of a mechanism that we perform on one of the model internals. So they give that general object a name, the interventional, and that generalization is really the technical heart of the paper. Okay, so once, the second, I guess, key contribution to that is once you have the more general language available in this framework, you can go back and write down these formal definitions of what we talk about in mechanistic interpretability. So polysemantic neurons, the linear representation hypothesis, the modular features, and graded faithfulness. And then you can kind of talk back and forth between those with a shared language. The third is, once you have that language, it turns out that every popular interpretability method is doing the exact same formal move. It's just aimed at a different part of the model. So patching, tracing, concept erasure, SAEs, steering, all talk or are all unified in this one way, and then we'll see how we can unify them later in the presentation. So we could start with something that I would say all of us have some kind of intuition for. Networks need a way to represent more concepts like facts, patterns, concepts, and distinctions than they have neurons available to spend on them. And it's just a resource constraint at that point. So what does the network do about it? Well, it doesn't give each concept its own private neuron because it can't afford to. So it lets the concepts share space. And you get a little bit of a blur between concepts in exchange for it to be able to represent vastly more of them than you would if every single one of them demanded its own dedicated direction. And that comes from Anthropic's toy models of superposition, which I think was actually the first presentation that Prism made last year. Okay, so now superposition has a symptom that you can actually go look for, and that's what polysemanticity is. The individual neurons end up firing for several unrelated concepts at once. And that matters because if a neuron participates in both concept A and concept B, then there's simply no clean way, I would say, to intervene on concept A without, or using a hard or soft intervention on that neuron, because you can't touch it without also touching B. And so the unit that classical interventions are built to operate on, that single variable or neuron, just isn't the base unit that these concepts actually live at. And so that's the fundamental problem that and the concrete failure mode that the authors are trying to address. And so everything that follows in the rest of the paper is really an attempt to build a theory where your unit of analysis is no longer that single neuron. Okay, so now the field already has an empirical answer to this, which is the sparse autoencoders that most of us work on, and I think it's worth walking through a little bit of what they actually do before we talk about what they're missing. The idea is that you learn to expand an activation into a much larger, mostly silent feature space, and then you can reconstruct the original activation back out of it. So its training would reward accurate reconstruction while keeping almost most of the features turned off for any given input. But if it works, each surviving feature is supposed to correspond to one concept cleanly. And empirically, that does work remarkably well, but how would we actually know that a feature that an SAE finds is real and not just one more arbitrary basis that happens to reconstruct the data well. Well, nothing in the SAE's training objective actually tells us that. It's optimizing for reconstruction and sparsity, but that's it, full stop. There's no sort of built-in notion of faithfulness to the network's causal structure itself. And that isn't a knock on SAEs specifically. It's the same question that applies to PCAs or probing or steering or any other interpretability method. So what each of these, or every one of these, is a proposed fix to superposition, and none of them on its own will tell you what it would even mean for the fix to be the right one. And so finding the answer that says, here's what it would mean for a fix to be justified, is exactly the kind of gap that this paper is trying to close. And I'll also come back to this idea. Okay, so part 2 is where we actually build the machinery.
1 second, Gia, there's a question.
Okay, go ahead.
Did they define concept in this paper?
Did you hear that?
Mm-mm.
Did they define concept in the paper? What does it mean?
No, but they do have examples. So they talk about distinctions, facts, patterns as cases of concepts, but they don't necessarily give you an account of it. I think that might be in one of their earlier works, but I'll have to go back and check.
And then another, can you go back one slide, please?
Mm-hmm.
So I think you said that you'll say more about this later, but I suppose just looking at that list of SAE, PCA, probing, and steering, to me, I mean, probing and steering seem like qualitatively very different things. Can you,
Yes.
I guess, what do those mean to you and how do they fit into this list?
Yes, so once the framework is developed, they sort of give you a way of parsing out each of the methodologies, and they put them in different categories, and don't treat them all in this one block. So I will have like 3-4 slides on that.
Okay.
Okay, so part 2 is where we would build the machinery to understand how they later categorize interpretability methods of all forms. So they start with causal models, interventions, and then they also build the abstraction relations that tie these different levels of description together. So we'll start as minimally as possible and then kind of build up from there. A causal model has a signature, which is just a set of variables and the values that each one is allowed to take, and also a set of mechanisms, which is one function per variable that tells you how the variable's value gets determined from the full state of the model. So here, x1 and x2 both feed into y, and then y's mechanism is just checking whether x1 came out bigger than x2. So 2 things that I'll also fly here is, and they'll matter in a bit, is the first is you would notice that the causal ordering between variables, what depends on what, isn't something that you assume up front as a graph. It just falls out of which mechanisms actually depend on which others. And that will be important for us. The second is that the solve of a model is simply the one assignment of values that is across all of the variables, that's consistent with every mechanism at once. And that's unique as long as the model doesn't have cycles in it. So like I said, when the model is acyclic. And so that's the whole ontology. And then everything from here onwards will be an operation that's performed on this object, the causal model itself. So what can we actually do with the models? Well, there's 2 kinds of surgery. A hard intervention fixes a variable to some constant. So you just reach in and clamp it, and then whatever mechanism used to determine its value gets ignored entirely. That's, for example, set the gender direction neuron to exactly 0. But a soft intervention is a little bit more general. So instead of a constant, you replace the mechanism with any new function of the model's state. So you could say something like replace this entire attention head's output with a different role. But notice that both of these interventions or kinds of surgery on the model internals are doing just the same conceptual thing at different levels of generality. They're both an operation that maps an old mechanism onto a new one. So this idea of mapping an old mechanism onto a new one is kind of the key that the paper wants us to pick up on.
Gia, there's a question.
Okay.
There was an assumption made about things being acyclic. Is that a big deal, or has most of the Mechanistic literature just dealt with feedforward models?
There's an assumption about being acyclic. I forgot the rest part.
And
Here.
is that because the Mechanistic literature is mostly focused on feedforward models, or is there something deeper?
Yeah, so the basic question is like the assumption of acyclicity, does it come from the fact that we are only interested in feed-forward models, or is there
Yeah.
like something other that's going on here?
Yeah, so they're predominantly looking at a feed-forward model in this. They haven't, I think they have extensions of this paper that discuss other models, but the primary case study that they will build and talk about is a feed-forward one. And then it's not necessarily that the framework breaks down when it comes to backpropagation or other kinds of, or other models or features of the models. It's just that once you have this shared language or framework, I think it's easier for them to build upon once they go. So the fundamental assumption here is that it's an acyclic one. I don't know if that helps.
Is this a general assumption about the abstracted causal model that we will end up with?
For this one, yes.
And so, for instance, we could apply this to a recurrent neural network. The causal model will still be acyclic, even though there's recurrence in the network, because the causal model is different than the network.
Yes. Yeah.
Yeah.
Okay. Okay. So, hard and soft interventions. Now, hard and soft interventions, both of them replace one variable's mechanism entirely. But if you go back to that idea of polysemanticity, then the concepts that we care about are spread across overlapping sets of neurons, and they're not neatly aligned to any single variable. But that also means that no single variable intervention would ever cleanly isolate to just one concept. And that is precisely the failure mode that SAEs are trying to work around empirically as one of the methodologies. So it just means that this standard toolkit that we have from causal inference, hard and soft interventions, is structurally or fundamentally the wrong shape for this kind of problem, and polysemanticity is the reason. So what we actually need is something that can target a quantity that's distributed across many low-level variables at once, while still behaving in a principled way, rather than just being an arbitrary edit. So that's exactly the definition that the authors are about to formulate. And that brings us back to the idea that I was talking about, an operation that maps old mechanisms to new ones. So if we draw out the logical implications of that one, that's what an interventional is, a rule that looks at what some part of the model currently is or currently does, and then hands back new behavior for it. So that is why a new behavior is allowed to depend on what was there before. And a concrete case of that would be a hidden vector into or if you rotate a hidden vector into a new basis, you edit one coordinate in that rotated space, and then you rotate it back. From the point of view of the original neurons, that's not a hard intervention on any of them, and it's not a soft intervention on any of them individually either, but it is an interventional. So hard here sits inside soft, and then soft sits inside interventionals, and the generality just keeps increasing outward, and that outer ring is really where the distributed SAE style, DAS style edits actually live. And that's the first of the paper's 3 contributions, this notion of mechanism replacement, generalized all the way to arbitrary mechanism transformation. But you should immediately be a little suspicious of this, because the space of all interventionals is enormous, and most of them are useless, because nothing so far is stopping an interventional from doing something entirely unprincipled on the model. So the natural question then would be, what actually made hard interventions well behaved in the first place, or principled in the first place, that we would want to hang on to as we get more and more general? The idea is that it comes down to these two properties. And the authors talk about commutativity and then left annihilativity. So commutativity is this idea that if you intervene on two separate or two different variables, the order that you do it in doesn't matter. You turn on neuron A and then neuron B gives you the same result as you turning on B and then A. And left annihilativity is this kind of self-explanatory idea, but it's that you intervene on the same variable twice and the second one is the one that wins. So if you set something to 5 and then to 9, it's just the same as setting it to 9 in the first place. So the move that the authors make here is that any collection of operations that satisfies both of these properties, commutativity and left annihilativity, even if it is nothing like the hard interventions on the surface, and even if it's operating on some derived signature of the model that you constructed yourself, it counts as an intervention algebra. So then they posit this theorem that actually makes it useful instead of just a satisfying observation, which is that any set of atomic soft interventions closed under composition automatically turns out to form an intervention algebra, which means that a well-behaved modular set of edits on a causal model isn't the special property that only hard interventions get to have, but it's something that you can go and check on for much stranger sets of operations, including the SAE style or DAS style ones that we'll talk about in a bit. Okay, so now we get to the central relation of the whole paper, and everything through the end of the theory section is a special case of this one idea. That is, a high-level model counts as an exact transformation of a low-level one right when a particular square always closes. So if you take a tweak down at the low level, run it through, or if you take a tweak, down at the low level, you run it through the low-level model, and then you translate it up into the high-level description, or you translate the tweak up to the high level first and then run it through the high-level model directly. An exact transformation is the claim that those two paths will always land you in the same position, no matter what tweak you started with. And so that's really the entire formal content of the idea that this high-level story is faithful to what's actually happening underneath. Not that it sounds plausible, not that it correlates with the right thing, because a commuting square either commutes or it doesn't. And so now we have a way of checking that. So they do this in two ways: a bijective translation and a commutative, or a bijective translation and a constructive abstraction, which we're about to look at, are both just the same commutative relation, this exact transformation, with an extra constraint on it. That is what the translation function is allowed to do. So once the square, we just let the square sit for the next couple of slides and we can come back to it. Most of what's left in the theory is just what kind of translation are we willing to allow on a causal model. Okay, so there's two forms of that translation, and the difference between them is really just the difference between changing your coordinate system versus simplifying your model. So bijective translation is the case where the translation is a perfect one-to-one correspondence between elements. It's injective, that is, every element in the set or domain maps onto a unique element in the second set or codomain. And then it's also surjective, so every element in the codomain is accounted for, which means there are no unpaired elements. So nothing gets lost, and it's purely a relabeling. And in the paper, they talk about this example where you rotate an activation space by 20 degrees, so two tilted axes turn out to be the same monosemantic direction. Same monosemantic directions where you have the same model, the same information content, and it's just a more convenient way of looking at it. And then the second kind is constructive abstraction, which I think is the more interesting case, and I want to say the authors do as well based on the way they talk about it, where the translation is genuinely lossy, right? So there are clusters of these low-level variables that they actually collapse into a single macro variable. And then the example that they talk about is where a network's 24 hidden neurons, or the hidden layer, abstracts into two intermediate symbolic variables of this tree algorithm. And that's no longer a relabeling, but a simplification. And it is a much harder claim to justify. So everything, or almost everything downstream that we would care about, including the worked example that they put out in the paper, is really just an attempt to earn one of these two relations, the bijective translation or the constructive abstraction. Okay, so if constructive abstraction is the interesting case, the natural next question is, how do we actually build one? How do we decide which neurons stand in for which high-level variable? And that's the job of an alignment. So an alignment groups the low-level variables into clusters, one cluster per high-level variable, and then a leftover group for everything that just doesn't matter to the higher-level story. So in the diagram, you see that a high-level model counts as a constructive abstraction of a low-level one exactly when it satisfies that same commuting square relation from the 2 slides back using this particular grouping. And I think this is actually the formal cache value of a sentence that's pretty common to hear, which is these neurons implement that symbolic variable. But that sentence isn't any longer a just so story if grouping those specific neurons and running the alignment produces the same behavior under intervention as the high-level model does. And if it doesn't hold up under intervention, then the alignment is simply wrong, which is a useful thing to be able to say that right now the field doesn't necessarily have, or what they were working on this paper for. And then there's one more piece of the structure before we get to the worked example. It turns out that any alignment, no matter how complicated, factors into exactly 3 operations, always in the same order. You marginalize, that is, you just drop the variables and you don't care about it in its entirety. You merge the variables, where you take several of them and you start treating them as one. And then the merge values, where you take a variable's fine-grained range and you coarsen it down to fewer categories. So there's a worked example in the paper that is a small network computing, quote-unquote, the larger of 2 numbers, where you marginalize away a redundant unit, you merge what's left into the single variable, and then you collapse its continuous output into a binary, which one's bigger flag. And then in 3 moves, they go from a numeric circuit to a clean symbolic comparison. And I find that useful more as a checklist, so the next time someone claims an abstraction, you can actually ask which of these 3 moves that they're making and check whether each one of them is separately justified. So then they work on the whole machine runs as an example, and yeah, so thus far we've been fairly abstract. So the task is that you're given these 2 shapes, these 2 pairs of shapes, the output is true if both pairs are equal or if both pairs are unequal. And so that's the hierarchical part, equality nested inside equality. There's an obvious high-level algorithm here where you check pair 1, you check pair 2, and then check whether those 2 checks agree with each other. And that's the 3 symbolic steps. What the authors then do is they hand build this feed-forward network. So you have the 8 inputs, the 24 hidden units, and then 2 outputs. And so that solves the exact same task, and they construct an explicit alignment of specific clusters of these hidden neurons, which are assigned to Y1 and Y2 in that tree. I will note, though, that they don't just assert that this alignment is the correct one. They run a bunch of interchange intervention experiments on it, and they confirm that the commuting square holds. So the tree algorithm here isn't, again, a just so story about the network. It's a verified constructive abstraction of it. So that verification step is what uses a specific tool that is really just the workhorse operation underneath most of modern interpretability work, the interchange intervention. And the, recipe is where you take a base input, you take a different source input, and then you set some target variables to the operations or to the values that they would have taken had you run the source input instead, while leaving everything else at the base values, base inputs values. So the idea is that you run the model, and what you get is the base computation with one piece of it swapped in from a counterfactual world. And there are two extensions of this matter that matter for us: the recursive interchange interventions and the distributed interchange interventions. So the RIIs chain these together, so a target swapped in value can itself come from another interchange intervention, and that's fully the mechanism behind path patching. And then you have distributed interchange interventions, which apply a bijective translation first. They do the intervention inside that new coordinate system, and then they translate it back. So that's exactly what a distributed alignment search, DAS, is doing, and we'll see that again when they categorize the methods. Now, exact transformation is a pretty strong claim because the square either commutes perfectly or it doesn't, and in practice, real networks and high-level stories almost never satisfy it exactly. So what we want instead is something graded, a score rather than a binary yes or no. And so approximate transformation is what they're working on to add these, or what they do to get approximate transformation is they add 3 ingredients on top of the same commuting square idea, which is a way of measuring how different two outcomes actually are, a choice of which swapped in values you're going to test, and a way of averaging the results across those many tests. So the specific version of this that matters most in practice is interchange intervention accuracy. And you could run a large number of models or interchange interventions on both the high level and the low level model, and you could count how many of their outputs actually agree. That fraction is the paper's formal stand-in for this measure of graded faithfulness. And it's kind of how they answer the question of how faithful is this explanation really. But what's nice about this is that with different choices for measuring and sampling, you also recover things that you already know, like probability difference, the logit difference, and like KL divergence, for example, as instances of the same general metric rather than a pile of unrelated ad hoc scores. So that is good. Okay, so part 3 is where we get to cache all of this in. It turns out that the framework is what sits underneath the entire...
Gia, there's a question. One second.
Okay, go ahead.
You have a sense of what the scores, the IA scores look like in some of the standard papers? What they're saying about what that plan would actually just...
What the IA scores look like?
Do you...
Is that the one?
Which...
Did I translate it correct? Yeah.
This is high-level abstraction.
Yes. See, the thing is, there's communication loss from there to here. So the easiest way is to get rid of the channel altogether and make the source closer to the microphone.
Okay. It's mostly an abstraction in the paper. Yeah, I would have to look more into that, so I don't have an answer for you.
I have a question about the interchange interventions.
Okay.
I guess it's just not clear to me what the high-level counterpart means in this case.
What do you mean?
I mean, so I guess maybe I'm trying to think of like a concrete example where the low-level intervention would be like to ablate a neuron in an LLM. Then you have this coarse graining that you do to have this high-level representation. I don't understand how you have one kind of intervention at a low level, but then the variables that you're dealing with at that higher level are very different. So I guess I don't understand how to what the high-level counterpart is. The high-level counterpart the coarse graining after intervening at the low level, or is there a separate intervention that you make at the high level?
So you could do it either way. Here's the... Okay. So you could translate it up and then do the high-level intervention. So there are two separate ones. There's a low-level intervention and a high-level intervention, and you can translate between them or transform between them. Probably the concrete example is the next slide that I'm talking about. It might have the vocabulary that you're looking for. Ask me the question in like 2 slides, and I might have an answer for you. Okay. So the vocabulary that I talked about at the beginning, where a polysemantic neuron is this like single raw unit that encodes multiple concepts, is a symptom of what we saw with superposition. The linear representation hypothesis says concepts are specifically linear directions in activation space, which is a strong and fairly restrictive special case. And so this paper's proposal sits one level up from both. A modular feature is any set of variables that performs an intervention algebra, commutative, left annihilative, and everything we defined earlier, reachable from the model's native basis by a bijective translation, whether or not it's linear. So in short, a modular feature doesn't have to be this straight line in activation space. It just has to behave like one under intervention. And that's a weaker, but I would say more strictly qualified and thus more defensible requirement than the linear representation hypothesis. And the best part is that it just falls directly out of the machinery that we've built so far and isn't an additional assumption of the theory. So here's where I think the payoff becomes really visible. And so this might help answer some of the questions. Everything radiating out from the causal abstraction in the center is a method that you use on a day-to-day basis, and each of them turns out to be this really specific instance of the relations that we've been building. So behavioral evaluations like Lime integrated gradients and then these SBAB-style concept effects turn out to be abstraction by a single input to output chain. Activation patching, causal mediation, path patching, those are recursive interchange interventions. So that's this. Where you chain them and then a target's fixed value can itself be the output of another interchange intervention. Okay. And then ablation. Go ahead.
Sorry, I just coughed.
Okay, I thought you had a question. Okay, so ablation, where you have concept erasure, subcircuit analysis, or causal scrubbing, those are abstractions by one specific 3-variable structure, and ablations are what we'll talk about in the next slide. Feature learning, PCA, SAEs, probes, and DAS are bijective translations, the one that's injective and surjective. And then steering ends up being what happens when you use an interventional, the most general kind, that was never actually validated as an interchange interventional in the first place, which turns out to be a substantive distinction and not just a technicality. But now we can zoom into 2 of these spokes. The ablation and feature learning are the ones that I'm going to talk about. Okay, so ablation or concept erasure, subcircuit analysis, and causal scrubbing, these are 3 methods that sound quite different from one another, but they're just operating on the same high-level model with different definitions of what counts as ablated. So the structure is the input X, output Y, and a binary Z that asks whether the concept was ablated or not. And normally Y would just mimic the network's actual behavior, but if Z signals that the concept was ablated in that binary, then Y switches over from the degraded behavior associated with losing that concept. So the translation function sets Z to 1 exactly when the low-level transformation broke the natural dependence between the hidden vector and the input. So what actually differs across these 3 methods, concept erasure, subcircuit analysis, and causal scrubbing, isn't the high-level model at all. It's just which low-level intervention gets to count as ablation. And once you see it that way, a decent chunk of the ablation literature stops looking like these 3 separate methods and more like this one method instantiated or implemented 3 different ways. Okay. The other spoke that I want to zoom in on, because it's probably the one that you use pretty often, is feature learning methods, all as instances of a bijective translation. Okay, so PCA rotates activations to find the directions of maximum variance, and that is, it's unsupervised, linear, and reversible by construction, so it's the cleanest case of the bijective translation. Sparse autoencoders expand into these larger, mostly silent feature spaces, and they reconstruct. But I will say they're only really close to a true bijective translation once the reconstruction loss gets near zero. The linear probes train a classifier on a labeled concept, and the direction that the probe learns becomes a candidate feature. It's not necessarily a feature, but a candidate feature, because finding a direction that predicts a label doesn't automatically mean that that direction is causally doing anything. And then distributed alignment search directly optimizes a rotation to line up part of the hidden state with a chosen high-level variable that checking the fit, where you check the fit using distributed interchange intervention. Okay, so the last one is kind of memorable, or the DAS is kind of significant because it's a little different in spirit from the other three. So DAS isn't just discovering an abstraction that you hope holds up. It is directly optimizing from the commuting. It is directly optimizing for the commuting square relation from earlier that I showed. So it, in a very real sense, is closing that loop between the theory and the method itself. In a way that the others may not directly be, or exactly be. Okay, so the unification buys us a more, I think, than the intellectual satisfaction of unifying some methodology. The first is this common yardstick, right? So you can now measure an SAE against a probe against a patching study on with the same terminology. For example, how good of an abstraction is it? How is it measured? Or how much does it cost? Or at what cost is it? Instead of comparing methods that weren't speaking the same formal language to begin with. The second is this real distinction between control and explanation. So steering, of course, can move a model's behavior without that intervention becoming validated as an interchange intervention, which means that you could gain control over a system while learning close to nothing about how it actually reasons. And then the third, the authors propose this as kind of a bridge across fields, which is what makes it somewhat relevant to what we're doing at Kempner. It's the same mathematics that's already used for abstract interpretation and program analysis, and for causal explanation of brains, of weather systems, of batteries, of epidemics, of economies. So before I do the takeaways, I don't know if that answered some of the questions that you had, but you could also ask again, and I may not have the answer again.
Maybe a quick clarification. I didn't quite understand the controller was the main explanation from there.
I cannot hear that, Sat.
I
can't.
Can you clarify more about the central point, the control not being equal to explanation?
Yes. Yeah. Well, just because you... Okay. Maybe I do this by way of example. Okay, so it's kind of the idea that this paper started out with. Maybe I should go back. Okay, so part of what they were starting off with is... This is before. Yeah, part of the idea is that a hard and a soft intervention can give you a causal explanation, a causal chain in that way. You could, perform a counterfactual experiment. You could say, apply you could either change a weight or an activation or something like that, and then get a particular output and say, well, now I understand that these particular counterfactual interventions have this outcome and have this effect on what I was originally planning to do or what I originally was doing. And so that in some sense gives you a description of what is going on, but an explanation, you want a theory to be able to map it out in terms of other things that you would do. So you don't want to just randomly experiment on a particular model internal without being able to compare it and contrast it with a little bit more of an abstract level about how they relate to each other. So the idea of being able to control but not explain is just you want a way to reason about it and not just control it. I don't know if that helps. Did it help or not, Shubham? I can't tell from the
Yes,
group.
yes, I think
Okay.
it does.
Okay. Okay.
You can go ahead, Julie.
Sounds good. So what I would say are probably 3 takeaways from their paper are, one is that faithfulness in mechanistic interpretability becomes this commuting square where translating up before you run the model or after lands you in the same place. And then 2, that interventionals extend the toolkit from a single variable surgery to distributed features, which is important because of the polysemanticity. And then intervention algebras are what keep that extension from turning into an unprincipled free-for-all, which is why we have the constraint on the interventionals that make them a little bit more well-behaved like the hard interventions. And then 3, you have one framework where you have that can characterize the translation plus the alignment plus the same commuting relation, all of which sit underneath the mechanistic interpretability methodologies. So activation patching, SAEs, causal scripting, DAS, and steering. And you have this one framework that sits under the entire toolbox. None of that makes mechanistic interpretability easy, to be clear. What it does, though, it gives us a way to be wrong about a claimed abstraction, which up until now has been pretty hard to pin down. So I think the paper does a good job of steering us, no pun intended, in that direction. So there are a few open questions that I'd love everybody's thoughts on, if you have any. Or if you have any more questions, I can answer those too. Or what I can do is ask those questions to Eric Bigelow, who was in my lab and just graduated. But he's starting at Goodfire and we'll be working with Atticus Geiger. So he can ask him and then I can respond and tell you guys. Okay, so here's some open questions. The first is that this kind of relates to one of the questions that was asked earlier in the presentation about feed-forward models. This is also only deterministic models that they're looking at. Cognitive science causal models are typically probabilistic, and so there is an open question of how much carries over from the noise. Another one that I thought was interesting is that this third one, the perfect low-level access is a disanalogy with the neuroscience. So would that mean that modern or machine learning interpretability claims outrun what the same standard could ever certify about the brain? So I think those are 2 interesting, but there's also more. Thank you. That's all I have for today.
Yeah, this is like, I was going through it. It's a very long paper. So kudos to you for covering most of the stuff that was in the paper.
Thank you. It's like 20 pages of citations, though, so don't overestimate.
It's always difficult to like discuss such a long paper in a given constrained time format. But I think you did a good job in
Thank
terms of
you.
like presenting everything. With that, like I would just open the floor for audience if they have questions or something that they want to comment on. Personally, for me, it's a very jargon-heavy paper. I don't work in this field directly.
Yeah.
So if I were to ask you like one question, in the sense like if you want the audience to take away something, like 1 or 2 takeaways from this paper that you thought, oh, this actually clarifies something for me personally,
Yeah.
what that would be, and can you tell it in like, yeah, that's basically the point. Like, what would that be? 1 or 2 points that you feel like, okay, this is something that the audience should definitely take away. This is something that enhanced my understanding as well.
Yeah, I think it's less a direct takeaway and more deciphering the paper and decoding the paper for me was how relevant philosophy of science and abstract algebra is to mechanistic interpretability, which has, for me, when I was starting out in interpretability, it was really intimidating to get through the technical and the, hard coding and kind of doing interventions on models. And visually, there are diagrams that make it easy to understand. Goodfire has some really good ones, and videos that show you the actual interventions and demos that you can play with. But I think the philosophy of science has a lot to offer, especially in terms of what counts as an explanation, like the question that was asked before about control versus explanation. I think philosophy of science has a really good amount of sources talking about what qualifies as an explanation. Why do we need explanations for scientific discoveries or theories, generally speaking? And then what abstract algebra serves as, or can serve as, is translating the heavy conceptual machinery of philosophy of science into the computer science. So I think, and it's part of why I chose this paper, to be able to move from concept to computation without losing fidelity in the explanation itself. So I think the methodology that they use and the way they go about arguing for this conceptual framework underlying mechanistic interpretability is a really solid methodology, and I'd like to see more papers that do that. It makes it easy for me, but it also, I think, does a pretty good job contributing to the field. So that's kind of my takeaway.